Finding your way with traceroute. In this MicroNugget, we're going to take a look at what traceroute does for a living and, behind the scenes, exactly how it pulls off this amazing task. Let's jump in. So let's start with our first objective here. When exactly would we even use traceroute? And the answer is simple. We want to know the path a packet's going to take through the network. See, for example, let's say you and I are sitting right here at this PC. We're going to send a packet over here to something on this network, 7777, and we're wondering, is the packet going to go this path through A, or is it going to go through this path, path B? And the answer can be given to us by using the command called traceroute. So let's find out which path is going to be used by using the tool called traceroute. That's exactly the time we'd use this command. Now, the first big challenge with traceroute on a Windows machine is how to spell it. T-R-A-C-E, and you'd think it'd be trace route, like it looks. However, because a long, long time ago, in a galaxy far away, the disk operating system only supported 8 characters. And so in the early days, traceroute was spelled T-R-A-C-E-R-T because they couldn't fit the 2 full words in traceroute. Well, even today, that's still the same command. So that's the first challenge. And then we're going to put in the destination network that we're trying to reach, or exactly in this case, a host on a network. When we press enter, it's going to give us a play-by-play detail of every single router that we've gone through to get to that destination. So if we look at this output, the very first response back we have was from R1. So our packet went out here, went to R1. R1 then forwarded it to R4, which went this direction. So it looks like path B, and then R5 right here, and then it finally made it to R7 directly, and that was our path. So it took path B. Now also, just to be aware that these names are showing up because we're using domain name system. Every time we hit a router, the DNS was used to give us the friendly name that matches the IP address on that router. So what if we destroy this connection right there, the bottom path, we disconnect the wire, or we turn off the interface? Will traceroute show us the truth about the new path? You betcha. Let's do that right now. So here's our plan. We're going to bring over the command line interface for router 4, and we'll take this interface, gigabit 2/0, and simply shut it down. To do that, we'll go into interface configuration mode for gigabit 2/0 and use the command to take down the interface, which is shut down. Now, in just a few moments, all the neighbors of R4 running the routing protocol are going to realize, hey, R4 is no longer responding to us and everything else, and that path will no longer be available. So now what's going to happen if we do traceroute again? Well, hopefully it's going to show us the path that's going through path A, and let's do it. Let's use the up arrow key, traceroute the same destination, and it's showing us the first hop is R1. Now it's going to R2, R3, the top interface of R5 to its destination. So now it's using path A as described by the output of traceroute. So that's what traceroute does for a living, and that's why we would use it. Now for the question of how. So let's take a look at the magic behind how the traceroute pulls this off. It's using a little something called TTL, the time to live. Now what is that? The time to live is a mechanism to help avoid loops on the network. For example, if you and I are sitting here and the network was not configured correctly, we might forward a packet into the network, and R1 may believe it needs to send it to R2, who thinks it should send it to R3, who thinks it should send it to R5, who thinks he should send it to R4, who thinks he should send it to R1, and then we have an endless loop. Now, the reason it's not endless with IP packets is because of the TTL. When we send a packet, we might send that packet with an initial TTL of 255 or some other number. It might be 128, depends on the application. But when that packet hits a router, the router takes the TTL and says, oh, it's going to be 255 minus 1. And R2 would say, oh, it's 254, the result, minus 1. So every single router decrements the TTL. If a router finally gets that packet and the TTL incoming is 1, it's going to say, oh, I'd love to route this packet, but your TTL is 1. I'm going to effectively change it to 0. The TTL is exceeded, and it's going to send a message back to the sender saying, I killed your packet. I'm so sorry. The TTL has been exceeded. So you might say, well, Keith, that's great. TTL helps with avoiding routing loops, but how is that used in conjunction with traceroute? We are tricking the network by manipulating the TTL inside of the traceroute packets that we send. So here's what's really happening behind the scenes with traceroute. When our PC sent out a request, the traceroute command, what it looks like to the network is a ping request, source from our IP address destined to the IP address of this destination we're trying to reach. And that's right here. Here's the source, 192.168.1.35. That's us, destined to 7777. No problem there, but check this out. The TTL traceroute set the initial packet of the TTL to 1, which means that when this packet, and we sniff this off the wire right here, when router 1 sees it, it sees the TTL of 1 and says, oh, I need to route the packet. Oh, but the TTL is 1, so it kills the packet, drops the packet. The packet never makes it to its final destination, but here's the magic. R1 is going to notify us that he dropped our packet. And here's what that message would look like. It's going to be a TTL exceeded message. So this is from the router at 1.111 to us at 1.35. And in the content, it says, it's an ICMP message saying, time to live exceeded. This is the reason I effectively dropped your packet. And that, my friends, is how we know who the first hop is in the network, is because he's the first one that reported. Now, if you'll notice, we actually have 3 entries here for the first hop, if you will. It's all R1 in this case. And what's happening is that when we get our first ICMP message back from 192.168.1.1, we measure the round trip time for what that took. We say, great. We now know who that first hop is because he's responding that he had to drop our packet. So what's with this guy and this guy? How can we have 2 more? We're actually sending out 3 of these ping requests with a TTL of 1. Why? Because maybe we have multiple paths, multiple next hops. We want to find out what those are. And also we can kind of find an average of the time. In this case, R1 is the only one in our path right here. So he responded 3 times. That's why we have 3 timestamps. And this is his IP address right there. This part where it says R1 is due to the fact that I have DNS configured and there's a name resolution happening in the background as well. So let's take a look at the second set of packets that were sent out by our PC. So if we take a look at the line 2 here, what we have is we have the next hop is R2. And how did we know it was R2? Because again, I sniffed the wire right here. This is where all these packet captures are coming from. The second set that we sent out, we had a TTL of 2. So R1 got the packet with a TTL of 2, decremented by 1, forwarded that packet to R2. R2 now has a TTL of 1 on the packet. R2 now sends an ICMP message back saying, oh, I'm so sorry, I killed your packet. And because of who we got the ICMP message from regarding the killing of the packet, that's when we know what our second hop is. In this case, it was R2 for all 3 of those messages. Now, in all of these examples so far, we've used this beautiful PC, a Windows PC. It uses, for its initial request for traceroute, it uses ICMP, the Internet Control Message Protocol. However, if we had sourced these packets from a router, like a Cisco iOS router, instead of using ICMP, it would actually use UDP as its layer 4 protocol, but the effect is the same. The TTL is still managed exactly the same across the path, starting with 3 sets of 1, and then 3 more sets of 2, and then 3 more sets of 3, until it can reach its final destination and determine the entire path. So in our journey, we've identified when we would use traceroute. That's if we want to find the path through the network. We also identified how the TTL is used to trick the network into feeding us back those ICMP TTL exceeded messages. And the last part is we discussed briefly about the protocols used within traceroute. I'd like to reinforce that. From a perspective of feeding back the information, the ICMP unreachable messages, those are always going to be ICMP. So whenever the router is telling us that it killed a packet, those are always ICMP messages coming back to us. For the initial traceroute, the Windows machine also happens to be using ICMP, and they look like ping messages with a TTL of 1, TTL of 2, and so forth as it propagates through the network. If, however, we are on a Cisco iOS router, for example, instead of using ICMP messages outbound, it would use UDP. Now at layer 3, the TTL mechanism works exactly the same. But if you ever get asked, what are you using for traceroute? Is it UDP or is it ICMP? Just remember that ICMP is used outbound by Windows and UDP is used outbound by a Cisco router. I hope this has been informative for you, and I'd like to thank you for viewing.